Our speaker for this afternoon is John Balboni. He is from the NASA Ames Research Center, and he's in charge there of what's colloquially known, to me at least, as the ArcJet facility. John has been working at NASA Ames for 26 years as of this year. He started there immediately after getting his degree from Cal Poly in mechanical engineering. And then he wrote here, with the benefit of NASA's support, he attended Stanford University and earned a Master's of Science in Mechanical Engineering. I didn't know you could get a Master's of Science in Engineering. So that was a great revelation to me. There's going to be a panel for the REU students in a couple of weeks about grad school. So I thought that was kind of an interesting thing that I wanted to point out to the students here. You can get a Master's of Science in Engineering, so who knew? And his emphasis with his master's degree was on hypersonic aeronautics. John now works in the thermophysics facilities branch as chief technologist and chief engineer at the ArcJet facilities. And in this role, his duties involve test operations, modifications, performance calibration, and design of new facilities. So in this work, he says he has enjoyed touching a range of NASA missions, from the space shuttle to several planetary entry probes to hypersonic aeronautics programs, all of which have made use of the ArcJet facilities.
I'm going to talk about, let me back up if I can, qualifying heat shields on Earth, starting with a picture of the space shuttle during its peak heating. It was at 55 kilometers, and it was taken by the Kuiper Airborne Observatory, which was flying at the same time and aiming its telescope, and got this picture of the shuttle showing the thermal image of the bottom of the belly of the shuttle and when it's being heated. I'll talk a little bit about that. And specifically what I do is electric arc jet testing. It's a plasma heated wind tunnel, a ground-based facility that's simulating thermal environment and flow environment of re-entry into the atmosphere of either Earth or any other planet that you can conceive of that has an atmosphere. This is a disk being tested in a hot flow stream in the plasma wind tunnel, the arc jet. And this is one of my favorite pictures from the Mars rovers. Now, it's probably the one that has the least amount of science information. The Opportunity actually spent a few days driving around the heat shield. So after the entry vehicle, this is on Mars, after the vehicle entered and landed on the planet of Mars, the heat shield had been a couple of kilometers away. It impacted here. You see this black trail? That's all charcoal. It's all the charred surface of the heat shield that just blew off of it and fell on the ground, and then it's now space junk. So what I'm going to do is give you a 45-minute discussion about space junk, the heat shield. It's important. And why is it important? Well, let's see. Most people are scientists, and they're interested in the science. The only reason for these missions is science. Well, the heat shield has an impact on science. It's 10% of the mass that's landed, say, for instance, in this case, on Mars. And for an 820 kilogram landing mass at $820 million, you can do the math, and it's extremely expensive to take a piece of space junk up there and set it and leave it to sit on Mars for eternity and do nothing. Of the order of $80 million of that mission was devoted to, well, in this crude accounting method, $80 million just to set a heat shield down on the surface of Mars. Well, it had an important function, of course, but its function lasted for about 5 minutes. And it's in the case of, say, for instance, the Galileo mission, that was an entry probe into the Jupiter's atmosphere. 45% of that probe was heat shield. In other words, dead weight. In other words, it was mass that was every kilogram that's mass of the heat shield is taken away from the mass of the science package over here, which is approximately 150 kilograms also. And so I'm going to talk to you about heat shields they directly impact on the mass of the science package that you can deliver with a spacecraft. And obviously, there's a great deal of pressure to reduce the mass of a dead weight like a heat shield. I mean, what is it? It's just taking away science At the same time, it's a critical single point of failure system on the spaceship, which we all were grievously reminded of in 2003 with the loss of the Space Shuttle Columbia, which happened because of the heat shield. It failed, and we lost the entire mission, and 7 astronauts were killed because there was enough damage in the heat shield. The heat shield failed. Heat shield then let hot gases into the structure of the vehicle, and the vehicle came apart, and it burned up in the atmosphere. And so at the same time you want to reduce the weight of heat shields in order to increase the science payload, you certainly don't want to reduce it to the point where it fails. And so heat shield design then becomes, it's an obscure area, but it becomes a rather important area for any science mission or any human mission that has to cross an atmosphere, whether it be Earth or another planet. And arc jet testing then touches on, say for instance, this is kind of a summary of a history of some of these programs go back to the 60s and the early 70s and the 80s and the 90s. So there are R&D applications for arc jet testing, where your materials, you have to surround these hypersonic vehicles with high temperature materials. So arc jet testing is how you would convince yourself that they're going to work. And you can develop materials, and excuse me, there it is. You can develop materials that would be used in different applications. You can also flight qualify, in the middle row, flight qualify materials. So now we think we know enough about arc jet testing that we're confident that we can actually say, yeah, for this mission, for any particular application, by arc jet testing and by evaluation, we can now say, well, with assurance that your billion-dollar mission or your human crewed mission doesn't have that much risk. It will succeed, or it has certainly a good probability of succeeding. And so these arc jets have been used for Space Shuttle and Apollo, Viking, Galileo, Mars, Pioneer, Venus, Magellan. I'll show you an image of Stardust that's pretty interesting. And also, we'd like to continue developing instrumentation. Again, it's just a dead weight. It's just a bulk that's carried along, but it's an important dead weight. And if we could instrument the heat shield and understand its performance, then on the next mission, we'll have information to gain more confidence and reduce the weight. It's also used then for space operations, supporting damage assessment, like on the Space Shuttle. Space Shuttle, it experiences damage almost every flight to the heat shield in some way or another. Some areas, they look like a shotgun was shot at the heat shield, and they get small little speckles in heat shield tiles. And arc jets are used to assess how much damage is acceptable, and also to develop repair techniques. And I want to acknowledge, please, that I'm plagiarizing desperately from other people's charts. Dr. Wright and Dr. Raish and Laub and Ernie Freder, they're all NASA Ames colleagues of mine. They're all involved in these areas that I'll talk about, and also Bonnie James at Marshall. They've had short courses, and they've given a lot of presentations, and I've used some of their charts in this. And I thank them very much, even though I don't believe I'm not sure that they know about this yet. But I'm gonna give you, say, 4 parts. First, what is the problem? Why do you need a heat shield, and what are the solutions for it? And how do you analyze it? What kind of experiments? And then the facilities, the arc jet facilities. I'll conclude with that. And so what is the problem? What are we trying to do? Well, as you all know, we're trying to explore the solar system. And you can do that remotely, and we do a lot of work remotely, but if you do want to have a presence, say, either on the surface of a planet or in an atmosphere, then you're going to be involved in the kind of work that I do. So there's Mars, there's outer planets, of course, we would love to go back to Titan. And we have an exploration of the moon. Now, the moon has no atmosphere, but if it's done with humans, the humans are going to return to Earth. So returning from either the moon or beyond the moon. And there's even an application called aero capture. Cassini, when it arrived at Saturn, you probably know this better than I do, but I understand it burned about a metric ton of fuel to decelerate and achieve orbit in Saturn. It's moving at a very high speed, hyperbolic trajectory to get to Saturn as quickly as possible. Now it's traveling too fast for orbit. Burn a metric ton of fuel. You know what it costs to take a metric ton of fuel to Saturn, 1 billion kilometers away? It's an enormous cost. And so there has been a concept around for decades called aero capture, where instead of using a propulsion to slow the vehicle and achieve orbit, say at Saturn, you'd use a heat shield and you'd actually dip through the atmosphere, just skimming across the top. There's pros and cons. It's a concept that's never been used because it has a very high risk, but it does have the potential for payoff of say, achieving a savings of a metric ton of fuel that you send it next time you go to Saturn. So those are all part of this thing. I have a video that I'd like to show you that's kind of interesting. It talks about the stardust. And it kind of gives you an overview of what I'm trying to talk about. It's 5 minutes long. I might skip a little bit ahead, and I'll try to narrate it. Maybe what I'll do is turn the sound down, and I'll narrate it myself. So I don't want to make Office better. Okay, there we go. Let's see. So this is about stardust, and it's a plug for Ames, and the Ames heat shield design. In that this mission and some other missions would not even be possible without the technology of a heat shield. Now, Stardust, I'll give you a quick intro. It chased a comet, Comet Wild. It was launched in 1999. It chased the comet. It flew through the comet's tail and with collectors, with panels that were extended and collected particles that came off the comet. So these are particles of the early solar system material, and brought them put them into a probe, and then the probe flew back to Earth and entered the atmosphere and landed on the Earth safely. And so it was a great success. Like I said, I'll probably skip ahead. It's a 5-minute video. So it launched in &99. This is a nice PR video. Sorry for being out of the view of the camera. And Dr. Sanford was heavily involved in the design of this mission. It flew to intercept the comet and was able to collect samples. Here's Dr. Sanford. He's one of the many people he's probably involved with SETI, involved in studying these tiny little. They return tiny little particles of stardust back to Earth for study. And here he's talking about, well, it's how we can learn about the early solar system. But so I'm an engineer. Here's the probe. So that after the samples were collected, they were put inside this little capsule, and the capsule flew back to Earth at a very high speed. And it required a technology that wasn't available until just before this mission. And here's an arc jet test, so that the part that I'm talking about is just the atmospheric entry, the last 3 minutes of the flight, of the 6-year flight, where without that last 3 minutes, though, of the technology that would allow this little tiny probe, it had to be very lightweight, to enter the atmosphere at very high speed. With arc jet testing, we were able to say, yes, this mission is enabled. This is enabling for Stardust. Without the right kind of a heat shield technology, you can't even propose a mission like that. So here is, this is a sample of the material that's tested in an arc jet. It's a small piece, probably about as big as a bread plate. And it's a special, some materials engineers developed this without Stardust in mind, but it became enabling for the mission. Here's the launch in 1999. Here's the reentry in 2005. It's an animation. But the thing is, as it flew over California, Nevada, and landed in the desert, they were able to observe this, and you'll see in the next picture. Here's the heating pulse as it dips into the atmosphere at 125 kilometers. It glowed brighter than the sun, although the capsule is only as big as 35 centimeters in diameter. This little capsule was glowing brightly at 100 kilometers distance, and they actually made now spectral measurements from an aircraft of the reentry during its reentry path at night. And so now they're able to get data on what was the spectrum and what was the state of the shock layer. And there's a bow shock layer in front of any hypersonic vehicle that's glowing brighter than the sun. And that then feeds back into, well, how well did we design the whole vehicle to begin with? So here they are now on a NASA aircraft instrumented with spectrometers and video, taking off from California, flying over to Nevada, and at the point of, I'll skip ahead just a little bit, at the point, you'll see then, you'll see a star appear. That's the Stardust, is that bright dot in the center of the screen. That's the Stardust as it It's dipping into the atmosphere. It's being heated, the surface being heated to 3,500 degrees Celsius for about a minute or two. I think it was about a 2-minute entry. Here it is streaking across the sky. This is a little 35-centimeter diameter probe that contains stardust. It contains comet samples flying across the Nevada desert. And then it landed softly, and they picked it up. Obviously, the scientists pulled it apart and are studying the samples from the comets. We took it apart and we're studying the heat shield on the outside of it, because this is a rare example of where we can actually take the heat shield after it's been designed, after it's been flown. We can cut it in half and section it and see how it performed, to then understand whether or not our heat shield design tools are valid or accurate. Because you remember, you have to add margin, you have to add extra thickness and extra weight in order to be sure that take care of uncertainties in the design. Well, how much margin did we really have? How much extra did we add on? It's nice to be able to know that by retrieving a vehicle like this. It doesn't always happen. You can't do that on Mars and Jupiter and Venus. But we were able to recover this spacecraft and study the most interesting part, the heat shield. And let's see if I can get back. Oh, okay, now I'm going to go ahead. And so, let me skip ahead to where I was. And so, oh yeah, so what is the problem? Why do you what's this whole business? Why do you need a heat shield? Well, it's because anything flying in space is traveling at a very high speed. The entry speeds are anywhere between satellite and escape speed for these different bodies. So you're talking multiple kilometers per second speed. That's a very high speed. And you all know kinetic energy is V squared, and it turns out convective heat transfer rate at the maximum on the body is V cubed. So these missions, as the speed goes up, you can see that the heat shield severity becomes greatly enhanced just by the velocity, by the fact that these bodies are traveling so fast. The Apollo entry, and then there's, NASA's working on a new lunar mission, and its entry speed is of the order of 11 kilometers per second. I mean, it's an incredibly high speed. And then, of course, the Jupiter entry was of the order of 59 kilometers per second. It's over 100,000 miles an hour. And without an adequate protection, then the inside of the spacecraft would be instantly overheated and burned up and melted. And how does that happen? Well, these are free flight photos. These are actually ground test photos of very small bodies, about 1 centimeter in diameter, 1 or 2 centimeters, launched by a cannon through a test pipe, a tube with windows and cameras. And these are special cameras that are called Schler, and they can take images of density gradients. And so the lines, for instance, there's a line in front of the blunt bodies. That's the bow shock. That's a pressure wave that's built up in front of the vehicle. And so that's the source. The source of the heating is the kinetic energy of the vehicle. The kinetic energy is transferred to the atmosphere through this bow wave. The pressure rises by a factor of 50 to 100, depending on the speed, depending on the shape. Factor of 50 to 100 pressure rise in just a few molecular collisions. Very rapid pressure rise as the gas is compressed on that bow wave. The temperature rises a factor of 10 to 30. So you have a very high temperature and a higher pressure gas generated in front of this vehicle that then washes over the outside. And that's what's heating a spacecraft, anything that's traveling that fast in the atmosphere. That's why you need a heat shield, because you've got a hot, almost, in some cases, an ionized plasma that's bathing the outside of the spacecraft as it's flying through the atmosphere. And the blunt body idea in the early 1950s was arrived at because it pushes that bow shock out and it dissipates that heat. It transfers actually a little more heat to the air, but it dissipates it better, and less of the heat actually transfers to the body. And that's why you'll see entry vehicles are all blunted on the hot side. Even the space shuttle is very blunt because it enters at a very high angle of attack where the flow is almost normal to the bottom of the space shuttle. It's pitched up at 45 degrees. And so it's also a very blunt body when it's during the peak heating. And these are representative of, what are we talking about? A shape of an aeroshell. An aeroshell is another word for heat shield. So inside this is the science package, and this is the heat shield on the outside. Here's a little one about the size of the Stardust. The Pathfinder was 2.6 meters in diameter. And the hot side is this blunt side on the left. And the little rover was inside here. And some other ones, this is Pioneer Venus on the left. It's also a blunted cone shape. Happened to be a 45-degree cone. The shape was optimized. I'll talk about shape optimization. The Stardust vehicle that we saw the video of, sitting on the table there, it's just that little thing you could hold in your hands. But the surface was 3,500 degrees C for a couple of minutes, protecting those samples on the inside. And these are all people that I work with in our division that work in the thermal protection or the heat shield business. And here's a big one, Mars Science Lab, scheduled for launch in 2011, 2 years from now. That big black circle behind it is a mock-up of, that's the size of the entry vehicles headed for Mars in 2011. It weighs, I think, almost 1,200 kilograms at entry. Maybe it's more. It's a very large and very heavy vehicle to send to Mars. It's the largest one ever been sent to Mars. And again, a bunch of people that I work with here, and there are also people from JPL and from NASA Houston and from Lockheed Martin who's building it. And so there's a rover that will be installed inside that. It's a large, one single rover, very large, the size of a small car, driving around on Mars hopefully in 2 years. So that's another project they've been working on quite a bit, is, well, all of these projects actually. And of course the Space Shuttle, which is now has 7 more launches and it'll be retired next year. So you only have 7 more chances now to watch it launch. And it has a variety of different materials depending on the heat, because it's such a complicated shape. And it has areas in the nose and the leading edges that are much hotter than, say, the areas on the leeward, the back leeward side. You're talking temperatures from 1,500, 1,600 C on the highest areas, I think even 1,700 C. And on the back it could be 600 or 700 C, literally at the same time. And with this complicated shape, then they actually develop different materials for different applications. But these are all, it's all part of the heat shield business. And so that gives you an idea of what are heat shields. These are all individual tiles, by the way. There's 25,000 of them attached to the outside of this vehicle. And they're reusable. I'm going to talk a little bit about the difference. This is probably the only one that I know of right now, the only vehicle I know of with a reusable heat shield. That means is that this heat shield, all of these tiles and all of these high temperature materials, not only survive the reentry, but they survive multiple reentries, and that was the whole purpose of the Space Shuttle, was to be able to fly it down, land it, reload it, and launch it again. And many of the pieces, although there's damage to some of them and they're replaced, many of the pieces on one of the Space Shuttles, any of them, have entered 25, almost 30 times. So they've gone through cycles of 30 cycles at these very high temperatures by flying back in the atmosphere over and over. So that's what's called a reusable heat shield, but this is the only kind. There's another kind of heat shield I'll talk about a little bit later. And how do you, an analysis is required. How do you know what material to use? What kind of heat shield do you need to use? How much do you need to use? And the analysis is interesting. It's closely related to the facilities that I'm going to get to in a minute. But and you could talk for hours on just this. But there are computational models, aerothermal models, which means the aerodynamics of the flight at high speed drives thermodynamics, and so they came up with this name aerothermal. So it's an aerodynamic and thermodynamic problem. So CFD is computational fluid dynamics. That's a tool that's been around for many years, but these are advanced CFD models. They don't just solve fluid dynamic flow and determine how the fluid flows over the surface. They also have to have thermodynamics included, because this gas is now rising to temperatures of up to 20,000 degrees Kelvin. And at those temperatures, you now have chemistry involved. Your species that are out in front of this vehicle here, the quiescent atmosphere, gets slammed into this shock wave, dissociates, turns into atoms, turns into different molecules, and recombines. So there's a chemistry effect, and the chemistry actually is also finite rate. It's driven at a certain speed that sometimes is slower than the speed of the vehicle. So so these are computational models that have to take into account, first of all, the various different atmospheric compositions, CO2, nitrogen, hydrogen, helium, and Earth atmosphere, depending on the mission, depending on where you're flying. You'll have shock layers with very high temperatures, possibly non-equilibrium chemistry. Now you have to resolve boundary layers, which can be millimeters thin, on a body that's meters in diameter. And now you want to also understand at the surface, over here on the right, the surface, all the gray surface is heat shield. And the gray surface is now, there's energy. There's energy flowing into the heat shield that's heating it. There's energy flowing out because it's radiating. There are species that are diffusing in and out. And so it's a very complicated science problem. It's a science engineering problem that's closely related to the facilities because of the same tools that are used now to evaluate even, let's say your surface of your heat shield had either a cavity or a protrusion. How does that affect it? Well, there's local high heating areas because of flow disturbances at these very high speeds. Your vehicle over on the left might have holes in it, say for retro rockets. These reentry vehicles, as they're flying in hypersonic speeds, they want to control them so they'll roll or pitch with retro rockets. So the heat shield will have holes in it, or it'll have protrusions from attachment bolts or cable connectors that pull off when it separates from the bus. You'll have a cable connector sitting out on the edge of the heat shield. So these are all details that you'd want to know how they're going to survive. And an arc jet test is, I'll get to that, is how you would evaluate these features on a heat shield. But the same computational tools will actually predict how the flow comes through an arc jet, a very high temperature wind tunnel, and how it flows over your model sample. You'll take a little piece of an arc jet, of a heat shield, and test it in an arc jet. The same computational tools as used in flight are used to simulate how does the flow come through an arc jet at very high temperatures. And how do you relate the ground test data to what's going to happen in flight? And another thing, too, if the flow coming left to right, or actually the vehicle is flying right to left, this hot gas comes through the bow shock, heats the front end. Well, it also flows around to the backside. And the backside has to have a heat shield as well, believe it or not. And this can be a very complicated flow, but it can have an impact on the weight of the vehicle if you don't design the heat shield properly. And now you're talking about computational models that take into account turbulence, radiation from this glowing gas in the back, flows that may be non-continuum. In other words, the number of molecular collisions gets very small. Separation of the flow and reattachment, and again, chemistry. And if you couple radiation or don't couple radiation, you get different answers. And so, in other words, there's a whole group of about 30 people devoted to developing computational models that are applied to heat shield design and to arc jet testing. It's very interesting. Now, I talked about reusable materials. There's velocity on the bottom axis and altitude. So a reentry vehicle like shuttle comes in at a certain velocity. What did I say, about 7.5 kilometers a second, and then descends and lands at 0. And it stays to the left of that big red line. In other words, the temperature of that heat shield is low enough, even though it's 1,800 C, it's low enough that the materials can be reused. But anything faster than that, you get to higher speeds to the right of the red line. You get much higher temperatures, and the materials all come apart. They all degrade in some way, and that's called ablation, or the material is called an ablative thermal protection system, or ablative material. And except for the space shuttle, everything is an ablating material, so I'll talk a little bit about that. And that's another area of computation and of modeling and of testing arc jets that you have to understand. An ablating material starts out, this looks like a layered material. No, it starts out a single material, a monolithic material. It can be a carbon-based or a phenolic-based material. But as it's heated, so there's hot gas, and this is a model of hot gas flowing over the top at 5,000 Kelvin. There's heat then entering the surface at the top. And then at the bottom is your spacecraft, where you either have a science package inside or you have people inside. They have to stay cool. And so this heating will create a char layer. It'll create a pyrolysis zone. And then you'll hopefully have this red zone, which is material that's still undisturbed by the heat. There's a tremendous amount of heat coming through, but you'll have the layer literally charring. You'll have the surface that turns black. It looks almost like charcoal. It may be actually being removed. You'll have decomposition, which creates gases, and the gases are migrating through. So computational models, again, you have people working for their entire careers trying to determine or trying to predict ahead of time how this material is going to behave when it's flying through the atmosphere, like you saw in that video, protecting the inside of the spacecraft. It's a challenging problem. And because there's so many uncertainties, then here's a representative thickness. Again, it's a cross-section of the thickness of a heat shield. This is just representative, but and it's also sort of scaled to where the gray area is the base thickness. That's the thickness that you would say if you knew everything perfectly, that's how thick the material would have to be to protect the inside. Well, you have to add on maybe 25 or 30% of what's called margin, or added added heat shield, which is extra weight and extra material, just because of all the uncertainty and the unknowns in solving these problems, in applying these to there's so many unknowns to the flight environment and to the material properties and material response. And arc jet testing feeds into that, because arc jet testing is really the only way to understand how a material is going to behave when it's subjected to a gas at 5,000 Kelvin for 5 minutes or longer, 10, 15 minutes. And so, experiments have to, I'll talk about experiments that have to do with arc jets. And so an arc jet takes a little piece of this flight environment when it's flying through the atmosphere and it's being heated by this compressed hot gas. You take a little piece of that vehicle and you build an assembly and you put it into an arc jet wind tunnel. So it's, here's an arc jet. It's an electric heated, plasma driven wind tunnel that which we have some over at Ames. And I'll talk a little bit about it, but an electric arc is discharged inside a tube. It's heating gas, generating plasma. That plasma expands through a nozzle and it hits your sample. And your sample now represents a piece of that spacecraft that's flying at high speed. You develop and characterize material properties under these reentry conditions. You can screen materials. You can take 2 or 3 different materials and subject them to the same environment to determine which one's going to behave better, which one has better properties. You verify design, specific designs, gaps and attachments and bolts and electrical connectors. You can characterize instrumentation and verify repair techniques. So these are all kind of uses for arc jet facilities. Here's another use of arc jet facilities, excuse me, is at the last minute somebody decided the Mars rover aeroshell, the heat shield on the Mars rover, needed retro rockets on the back side. So the hot part is the left side, the heated part is the left side where the hot gas is hitting, expands around the corner, and somebody said within about 8 months of launch, they said, by the way, we need retro rockets because we need to be able to steer this thing while it's flying through the atmosphere before the parachutes open. And so at the last minute, then the computational tools were brought out. What does it do? They have to have these bumps. Now these retro rockets now had to be added on with literally a protrusion. And then how is that affected by the flow? And then in an arc jet on the right, how does the flow then going to be simulated on the ground in an arc jet test using the computational tools? And then on the lower left, we ran arc jet tests. Here's a photo of an arc jet test with hot gas flowing over this it's called a TERS cover. It's a cover over the retro rocket. And then comparing the data to the computation, and everybody then decided, yes, we're okay with this. This is a good design. We think this is not going to affect, it's not going to cause this to crash. It's not going to cause it to burn up. And so they went ahead and built this little cover. It was about 6 inches long, 4 inches high. And there are 3 of them. And they mounted them on the backside of the MER. So that's kind of a practical application of modeling and arc jet testing for a practical application of, say, the MER rovers. That's the Mars rovers that entered in 2003. And here's an arc jet test application. It's a repair technique. After the Columbia accident, NASA said we must have a way of repairing the heat shield in flight, in orbit, with astronauts wearing spacesuits in the vacuum of space. And so this is a process of almost maybe over 2 years of deliberately drilling holes in heat shields and then figuring out patches or covers, ways to plug holes so that the hot gas, the gas flowing over it, again, 4,000 or 5,000 degrees Kelvin, and the surface reaching 2,000 C, you had to be able to have a patch that an astronaut with gloves on could apply, could turn down, could seal around the edges. And then we tested it in arc jets for 15 minutes and qualified it. Now this is the culmination of 2 years of testing with a successful repair, but there were a lot of ideas that came before this that were tested that failed in the arc jets. So they weren't even, obviously that was then, those are concepts that were dropped because without arc jet testing, though, there wouldn't be any way of knowing if a repair technique is even viable. So these are patches, or they call them plugs, but I consider it more of a patch that could cover a hole in the space shuttle wing leading edge that are stored on the space station right now. They have a whole suite of them. In case shuttle is launched and arrives at the space station and they find that there's damage to the heat shield, they now have repair techniques that are tested in arc jets. And they have pretty high confidence that they could avoid what happened to Columbia if it happens again in the future to another space shuttle. And then facilities, as far as arc jets go, that was kind of the whole purpose of this talk, wasn't it? Is our Ames has a block-long complex called the arc jet complex. All of this equipment, I point this out, there's infrastructure in the center here. There's a vacuum pumping system with cooling towers and a giant power supply that feeds power directly from PG&E. All of this equipment and a group of people is used to test. Remember that piece of heat shield material was something you can hold in your hand, the size of a plate. So it's a highly energy, it uses a lot of energy, energy consumptive. And that's because the energy density of a gas flow, or energy density of the flow during reentry, is very high because of that high kinetic energy and the high speed of the vehicle. And so in order to reproduce that on the ground, you need a tremendous amount of energy. So we're feeding multi-megawatts, 60 megawatts of electrical power off the grid into the arc heaters. We're using high power to run all this equipment to test that piece of material that you could hold in your hand for 15 minutes. And that's the kind of scale that's required to do a relatively small scale arc jet test. Here's a test. Here's an arc jet which flows over a panel, a flat panel of space shuttle tiles. The upper view is a side view with the flow going left to right, and the right view is looking down with a thermal imager. So you're getting. Here's an idea of what you can do: is get a thermal image. You get a map of the temperature of the surface and also the temperatures in the gaps between tiles. You can see individual tiles here, these squares. And this can be as large as 80 by 80 centimeters. Now that's one of the largest test articles you can test in an arc jet, but again requiring up to 60 megawatts of electrical power in this one facility just to get an area that large heated to that temperature to evaluate its thermal properties. This is how an arc jet works in schematic. It's a tube with anode and cathode, an anode at one end, a cathode at the other end. So those red bars are anode and cathode. And down the center of the tube is an electric arc discharge. It's DC, so it's continuous and can run for 30 minutes. So with that discharge on, then you introduce your test gas. Typically, air and nitrogen, or air or nitrogen, introduced into that tube will be heated by that electric arc. You could heat any gas. You can heat CO2 to simulate Mars and Venus. And in the past, we had an arc jet that was heating hydrogen and helium for simulating Jupiter entry. And that test gas in the arc heater is then expanded through a nozzle, which accelerates it to high speed, supersonic speed, into a chamber, where there's a test article that the flow impinges on. And I deliberately showed a little tiny test article in the schematic. It is really a small part of this large facility. The chamber is evacuated because we're simulating high altitude flight, 30 to 60 kilometers altitude on Earth. Gas temperatures, again, there are thousands of degrees Kelvin. And it's a very highly energetic flow. And this is a high voltage device. The arc heater itself, the discharge where it's heating the plasma, is a high voltage device. I have some pictures here. We actually have 4 of these arc jets running at, they don't run at the same time, but they're all they're operational and they can be run back to back during the day. There are 3 20 megawatt facilities, left and lower right, that have different capabilities and different, they simulate different aspects of the flow or the vehicle. And then there's a 60 megawatt facility. It's a scaled up version in the upper right. And what these high power levels do is they buy you heating more gas, which gets you a larger test area. But again, large test area, we're testing samples that you can hold in your hand. So we're only simulating a little piece of that big vehicle. And that, again, while I talked about computational tools, we rely on computational tools to take a little bit of data that you get out of these big facilities to scale it up to the actual full flight case. And here's a team of people. So this is a typical team that would run one test. This is back about 3-4 years ago. But that's a team of engineers. There's test engineers. There's a principal investigator, the person who comes in who's responsible for the research results. There are technicians who are mechanical technicians, electrical technicians, instrumentation technicians, and they're operators of all the other equipment that you saw in that aerial view. So it's a pretty labor-intensive group, but it's a really good group to work with, and people are really dedicated, and people have been working there for many years, and they really put themselves out there. The people really love their job because they love how they're impacting these different programs. And I have another video to close out. I don't know why it's not going to the next one. Oh, this is just a collage of these are different ArcJet samples. The top ones are obviously slender hypersonic bodies that are made out of carbon that they're intended to last for long periods of time. In fact, there's a picture of it in the stream. This streaky color that you see is the flow, the bow shock coming off of those models. And these are what we affectionately call hockey pucks. Pretty much the rest of them, they're about the size of, they're 3, 4, or 5 inches in diameter. And they're oriented so that the flow hits them directly on the flat face. And what you can do is you can instrument them, you could drill holes in them, you can repair them, you can even make them in the middle here out of 2 different materials with a gap in between. You can study how if you had to tile these materials on a large surface, how the interaction between the gaps in between materials are. And you can see before pictures on the left and then after pictures pretty much on the right, where the material behavior on the first 2 hockey pucks is pretty good. This gap actually protruded. The gap material survived better than the parent material. And then this one on the bottom is an example of a material that failed. So it's interesting to show, or for you to understand, that some of these materials, they'll bring them in, you heat them up, and they just fall apart and they melt and they don't perform at all in a way that you would want them to. And so that's an example of a material that's gone into the dustbin, is that lower row where the material just slumped. You can't fly a spacecraft where the heat shield would slump like that. And that's why you do ArcJet testing. And I just have another video. Hopefully I'll get that to go, and I'll show you what an ArcJet test looks like. In fact, I'll just go right to number 3 and show you. This is about a 2-minute video that shows a wedge test in an ArcJet. So a wedge is literally a wedge-shaped model holder, and you'll see 2 views of the same wedge, first from the top, and you'll see this hot gas flowing over it, like literally a wedge-shaped model holder. The wedge contained what was called a shuttle tile. It's a reusable tile. It didn't ablate. And you start before the arc starts, and then you'll see a flame. There's the arc. The power button is pushed, and the arc came on. And now you'll see the model swing into place right there. Now you see the streaks are the bow shock, supersonic flow. This is skipping ahead a couple of minutes. This is about a 5-minute test. And so the flow is established. The power levels are adjustable in the ArcJet. And the current and the power can adjust. So now you can adjust the temperatures on the surface of the model. And the test surface is actually normal to the screen. And you'll see it in the next section. So you're adjusting the power levels and the time and the duration and the location and the angle of the wedge. This is at a higher power level. Later on, almost to the end of the test, the model is glowing just absolutely white hot, about 1,500 degrees C. There we swung it out. The test is over. And you'll see the same test from the side view. So you get a view now looking directly at the test piece. And I'll show you that in just a sec. Again, the arc is not on. We're looking into the test chamber. The arc just struck. The flow is left to right. And then as the model is in the near field, swings into place. Now that black square is the test article. It's a sample of shuttle tile. It's inside of a water-cooled holder. That holder is all copper with high-speed water flowing through it to prevent it from melting. It is being spattered, you can see, by there's debris inside the arc heater. That's one of the drawbacks of ArcJet testing is contamination in the flow. That does clear up in a little bit, but you can also see that test panel is now glowing. It turns from room temperature to glowing bright orange and even white hot. This is actually white hot, but the camera has been stopped down and you can't quite see it. So that's an example of ArcJet testing of, say, of a sample that can be swung in and out of the stream. You can control the power levels and the temperature levels on the surface and the time that it's exposed, so that you would be representative of whatever your flight application is, from space shuttle all the way to planetary entry probes. So the conditions can vary very greatly. And that concludes my talk. I thank you for all sitting here and listening. and then I'll take questions of anything I can possibly answer.
Well, I'd like to start with a couple of questions then, John, if I may. You showed us the multi-layered effect of heating, and you said this looks like there are many layers, but this was originally all one piece.
Mm-hmm.
And I was wondering what the scale was on that slide.
Yeah, that was a cartoon.
Or a cartoon. I don't know if you can pull it back
No, I mean,
up.
yeah, okay. And so that, yeah, in other words, the relative thicknesses of the different layers.
Right.
Let's see, I can bring it back up. And I guess the answer, though, is it all depends. It would depend on the heating rate, how much heat is flowing in at the hot surface, and for how long. Let's see, that's not how you do it. Oh, we're starting at the beginning. And so that was, let's just skip ahead. So the different missions have, remember that there's the heating rates vary over a couple of orders of magnitude depending on the mission. Like the Galileo mission had extremely high heating rates for flying into the Jupiter's atmosphere at such a high speed. And in that case, then the char zone would have very quickly have grown to be a majority of the actual heat shield thickness. And so we're talking about this is the extreme case, the maximum case, Galileo, the worst case entry that's ever been done. It was 14 centimeters thick at the thickest point, at the nose. And it actually, not only did the char layer grow to be the predominant, but it actually then was eroded away. The final thickness was something like 8 or 9 centimeters. So it lost almost half of its thickness due to not only char growth, but then erosion and what's called recession, where the material actually gets thinner. So that's the very extreme case. For a case like a Mars entry, which is actually a relatively benign heat shield entry application, you'll get a char layer that grows. It might only be 10 or 20% of the total thickness, and the thickness would be of the order of maybe 5 centimeters. So so it can vary very widely. That char layer could be a significant part of a very high heating rate case, or it could be just kind of a thin char layer that develops at the surface. And it's actually could be stable. It can turn into a stable char layer.
Now, those numbers you're quoting for me, though, are those are model numbers? Those you didn't get those heat shields back.
No, but those are the design values. Though. I mean, so when it left the Earth, we know how thick it was, and so it was say of the order of 2 to 5 centimeters for a Mars entry vehicle. They're about 2 to 5 centimeters thick, and the char layer might be just a half a centimeter after 5 minutes. Because again, the Mars entries are actually relatively benign. They're kind of like almost like a space shuttle entry in terms of the heating values. They're relatively mild. And when I say mild, though, there's still enough heating that would melt pretty much any material. But as far as heat shield materials go, it's relatively mild. And
the CFD model has its own limitation with aerodynamics, and I wonder how reliable is it with the aerothermal component?
Yeah, that's
to count on it fully without maybe to compare actual testing to those findings from the models.
Oh yeah, the CFD people are clamoring for data, for validation data, and you know, they would. The best alternative for the best source of validation data for the CFD models that are computing this highly complex flow and material response would be to do a flight test. And a flight test is the most expensive way to do it, hundreds of millions of dollars. So we're always pushing for doing flight tests. But it's difficult to do a flight test when you're talking about Mars or Venus or Jupiter also. The mission is what it is. And so we're pushing the idea of instrumentation. We actually have a whole group, now a small group, of people who are designing instruments where you actually will instrument in depth into the heat shield material, and now you'll get data back. Hopefully you'll radio the data back to Earth, so that you'll now get a measurement of the temperature growth through the material. You'll get you can actually measure the char layer growth. You can measure the thickness as it recedes. We have developed all these instruments. We're having a really hard time getting them onto the missions. There will be some instruments though on the MSL, the Mars Science Lab in 2011. That'll be the first time we get in situ data from Mars on the heat shield. Because nobody's interested in the heat, how the heat shield performs, except that they don't seem to realize that it has a direct impact on the science. Because if you can reduce heat shield mass, you can increase the science payload. But it's such a long payoff that it's difficult to get people to buy into that.
So you basically couldn't really count on the aerothermal analysis from the model?
Well, so we use arc-jet testing to gain data. So now you need to understand the arc-jet flow environment. It's a completely different flow environment, by the way, than the flight environment. It's a heated plasma that's impacting at a lower Mach number and completely different conditions, although it's simulating the right energy levels and the right heating levels. So we're using arc-jet data, and we can use, there are some other facilities, shock tunnel facilities that can generate very high speed, high temperature flows. So we use ground test facilities as much as possible to you squeeze every little bit of information out of ground test data, because yeah, you're right, these complex models require a lot of, require some very detailed data to validate them. Otherwise, how do you know that you could crank out a result, but how do you know how good your results are? Especially with such complex physical modeling going on. Oh, we also, I should mention, we do have some non-intrusive diagnostics of the arc-jet. We're actually trying to, and we actually have lasers emission, and we have laser absorption and laser-induced fluorescence experiments, which are making spatial resolve measurements of what the flow field is like, the status of the gas, and down to the molecular level. What is the state of the gas in the arc-jet, which is fed back into the computational models, because they are actually resolving the chemistry down to the molecular level. And so we're doing everything we can to validate those models, because we hang everything on the validated model, or on the computational models. Everything relies on that.
Could you tell us a little more about how the gas is accelerated? Because I take it it's a neutral plasma.
It's pretty much a neutral plasma.
So how does the gas get up to those very high speeds?
Well, it's a matter of pressure. I guess I didn't mention, like, say, for instance, inside where the tube where the arc discharge occurs, and you're generating very high temperature gas, it's under pressure from anywhere from 1 to 10 atmospheres. And some arc jets, 1 to 10 atmospheres. So you have a high pressure, and then you're squeezing it through a supersonic nozzle into a vacuum chamber. So you've got this pressure ratio across the nozzle from upstream to downstream of 1,000, factor of 500 to 1,000. That's pushing the gas through the nozzle, and the nozzle itself accelerates the flow. In exactly the same way a nozzle on the bottom of a rocket accelerates the flow out the bottom of a rocket, which pushes the rocket. This is a rocket too on it setting on its side. And we're accelerating the flow just by the pressure and the shape of the nozzle. And we're accelerating to Mach numbers between about 3 and 8. So you can get about a Mach 8 flow in an arc jet.
So there's no electrostatic
yeah, there's
forces.
no push. That's been studied. There have been a lot of, back in the 60s, before my time, they put in magnetohydrodynamics, where they actually are then applying magnetic and electric fields to accelerate the flow, and I guess there was limited or even no success in that sort of thing. But people are still always talking about electrostatic and electromagnetic accelerators added to a facility like this to get even more energy out of it. And that would be a useful thing to have if you can make it work.
So those big spheres we see over at Ames, those are the vacuum?
Yeah, those are used for vacuum.
Yeah.
Yeah, you pump all the air out.
They fill up with, how long can they hold the vacuum when you're...
Yeah, they slowly fill up with air from the wind tunnel, as the wind tunnel is filling them up. But you can maintain there's 4, you see those 4 out there, you ever seen that? There's 4 of them that are tied together. There's a really big wind tunnel, the 3.5-foot wind tunnel that hasn't run now for 15 years. It's been shut down, but it used to run into those spheres, and it could run for a minute or two while the vacuum level is slowly rising, and then it gets up to a point where you have to shut off the test. So those spheres are used for vacuum, but in our case we have a vacuum pumping system that's continuous and can pump for 30 minutes or to an hour. It can pump for an hour using, I didn't mention it, I didn't even describe it, there's a steam ejector system. So steam is generated, it flows through a supersonic nozzle through venturis, and just with no moving parts we have a vacuum pump by steam flowing through a series of venturis, very large venturis that you could walk through. But steam flowing through Venturi is actually used to pump down the arc jets.
One last question, which was, John, you said a couple times that these were unique facilities, and I noticed at the end of your slide, at the end of your presentation, you had a slide that said there were 2 other NASA and 1 other DoD facility like this. Is that right?
Yeah. Unique at Ames is the scale, and the power levels are higher than the other facilities. It's unique because of the high power and the very large size. But NASA Houston has an arc jet lab that is a 10 megawatt size, and so they're doing exactly all of these, everything that I described to you is being done there, but the models are smaller. So instead of being 5 or 10 inches, instead of being 20 centimeters, it's 5 centimeters, and so they're doing it in a smaller scale. They're heating less gas with lower power, but they're heating it to the same energy levels, same Mach number, same power levels, and they're investigating all of the same, everything I talked about, but in smaller scale. And it's just more difficult to scale from a 1 centimeter, 2 or 3 centimeter body, the data that you get from that versus a 10 or 20 centimeter body. So there's 2 facilities that are NASA facilities that are arc heated wind tunnels, and there's 1 DoD facility. It's in Tullahoma, Tennessee, and they do missile nose tip testing mostly at very high pressure. So it's an arc heated facility, but it doesn't have any overlap to the NASA facilities in terms of its testing capability. It uses the same principle of an electric arc to heat a gas, but it's such a different flight regime to test ballistic missiles that we cooperate together, but we don't have any overlap. So we don't, we can't exchange workloads and things like that between our facilities.
Okay, so briefly, 2 other clientele that immediately come to mind would be U.S. industry and international partners. Presumably ESA, the European Space Agency, has facilities like this that they use for...
They absolutely do, yes. That's a good point. Yeah, we have a pretty good relationship with... so in Italy, they just built, or not just built, in mid-1990s, it's been 15 years now, they built a large arc-heated facility. It's almost a direct copy of ours. It was made by Aerotherm, a company in Mountain View. Right, God, they were right down the road. They literally copied the Ames arc jets. So they installed a very large 70 megawatt size arc jet in Italy, in Capua, or near Naples. And we try to keep in touch with them. They don't have a whole lot to say. I don't think they have a whole lot of business going on right now. They, the European, everybody's economy is down, and the ESA budgets are down. So they have a big facility in Italy. They have some smaller facilities in France and Germany. And every once in a while we always get together at the international symposia. And so we do exchange ideas, information, and results to the degree that we're allowed to by the international trade laws. But so that always gets in the way. But that's always it's a nice thing to do, is to maintain those relationships and get business trips to Germany and France and Italy.
Well, as a token of our gratitude for John taking his time to come and give us this talk today, we'd like to give him a SETI Institute pin.
Oh, thanks.
And please join me in thanking him one more time for his talk.
Thank you.